The final talk of this session will be a wild byte bootstrap for degenerate kernel tests. And it is from Kasper Churalkowski. I hope.
Good enough.
Okay. Dino Sadinovic and Arthur Gretton, and talk will be given by Kasper.
Good afternoon. Today I'll be talking about wild bootstrap for degenerate kernel tests. And that's a work I did together with my supervisor Arthur Gretton and with my colleague Dino Sadinovic. And one of the problems we'll be trying to answer today is whether the distribution P and Q are the same. So the way we get access to the distribution P and Q is by looking at the samples. And the twist to this problem is that the samples that we get are not independent. So we get access to the samples that come from the random process. So the way usually people think about this problem is that they get independent observations. And this kind of problem is called the two-sample problem, and we'll be trying to solve it using the maximum mean discrepancy. I've said that just one type of the problem we'll be trying to solve, and this is because of the fact that the method that we're proposing in our work is more general. So the wild bootstrap method does not only apply to the two-sample test, but one can also use it for the independence test, such as Hilbert-Schmidt independence criterion, or to assess the interactions between three random variables. So the requirement that we put on the statistical test that we'd like to perform is that they need to use kernels. That's what we got, the degenerate kernels. And I'd like to leave you with this, the impression that it's more general method than a method that only applies to this two-sample problem. However, I will mainly discuss the two-sample problem in this presentation since it's, I'll say, the easiest one. So before I tell you how to solve the two-sample problem using maximum mean discrepancy for the random processes, I'll try to sketch the solution for the IID observations. And this is important because that will give you the insight into how does the method works, and that insight generalized to other types of tests. So as I've mentioned, the maximum mean discrepancy is a kernel test. So our take on that problem in here is by looking at the similarities. We look at the similarities by using the kernel function, k, and the kernel, the simple interpretation of the kernel is it is a function that measures a similarity. So what we do here is we create the similarity matrices, and they measure the similarity between the points from the blue distribution, distribution P. They measure the similarity between the points from the red distribution, and we also measure the similarity between points from P and Q. So that's like an intersimilarity. And once we've measured this similarity, we can plot it, and then we can also put those similarity matrices together to obtain the gram matrix. So it turns out that this matrix looks different in a case these two distributions are the same, and it looks different in the case when those two distributions are different. And you can see that visually, but the question is how to quantify that difference. And the way that MMD deals with this quantification is by looking at the average similarities. So what we do here is we look at the average similarities within the samples from P. We add to that the average similarities within the samples from Q. And we twice subtract the average similarities between P and Q. Turns out that what we get is a single random variable called V statistic, and this V statistic got different distribution in case when P is equal to Q, and different distribution in case when P is different than a Q. So if P is equal to Q, under the null hypothesis, we got the red distribution. So that's a spiky distribution. It's greater than 0, but it's still somewhere around the 0. In a case when P is different than the Q, we get somehow flatter distribution. And as we see more samples from P and from the Q, this blue distribution got even flatter and closer to 0. So the distribution of V statistic is different when P is equal to Q and P is different than Q. However, we again need to somehow distinguish between those two cases. And we do that by coming up with the notion of like a threshold and performing a statistical test. So the good threshold is such that if we see our V statistic on the left-hand side of the threshold, it is more likely that it was drawn from the red distribution. And if we see it on the right-hand side of the threshold, it is more likely that it was drawn for the blue distribution. And based on that, we make our decision whether P is equal to Q or P is different than a Q. The problem is how to choose the threshold, and here we've chosen threshold to be a high quantile of the red distribution. In this case, 95% quantile, so 95% of the mass of the red distribution is to the left-hand side of the threshold. Well, now we've defined how to what should be the threshold. However, we don't know how to calculate it because the distribution of the V statistic when P is equal to Q is difficult. That's an infinite sum of the weighted chi-square variables, and we cannot really analytically compute the quantiles of such a difficult distribution. Therefore, we need to use other methods, and what we'll be using in particular and what was used for the IID observations are the permutation tests. So in permutation test, we generate the vector W that consists only of plus ones and minus ones. And we've got exactly half of the vector W are plus ones and half of it are minus ones, but they are allocated randomly. Once we've generated the vector W, we generate a bootstrapping matrix that is simply W transpose times W. We take the bootstrapping matrix and we multiply it with our Gram matrix, but we multiply it pointwisely. And as a result, we get yet another matrix which resembles the Gram matrix in a case when P is equal to Q. We'll try to see how this visual similarity transfers to the similarity of the distributions. So again, we take our Gram matrix, we take our Bootstrap matrix, and we define the Bootstrap V statistic. And it turns out, and it can be proved, that the distribution of the Bootstrap V statistic, V and P, converges to the true density of the V statistic. And as a result, the Bootstrap threshold converges to the right threshold. So now we've got a way to actually approximate the correct threshold, and therefore we can perform a statistical test. Now, going back to the difficult problem, we've described how to solve the two-sample problem when there is no temporal dependency within our samples. And now I've just added the temporal dependency to our sample, and we'll see what will be happening to our V statistic and how our test will change. Turns out what mainly drives the distribution of the V statistic when we're working with the time series is the memory of the process. So here I've plotted two random processes. These are two autoregressive processes. And one of them's got a small memory, and the other's got a large memory. So Q's got a small memory, and in this case, the memory can be simply expressed in terms of the autoregressive coefficient, which is written in red here. So Q process got the autoregressive coefficient equal to 0.14, and the Z process got the autoregressive coefficient equal to 0.97. You can see that for process Z, you can quite easily predict the next value given the previous value. On the other hand side, the process Q looks much more like the random noise, and it's more difficult to predict the future values. And that gives us the notion of the memory, simply how much does the process remember about its own past. So in the paper, we defined the memory for all kinds of processes, not only autoregressive processes, but to understand the effect of the memory on the V statistic, it's sufficient to study the autoregressive processes. So let's look what happens if we plug in random processes to our two-sample test rather than IID observations. So if the memory is very small, almost no memory, I would say, there is not much difference between the threshold that we get from the bootstrapping procedure and the threshold the correct threshold, the threshold that we get from the true density of the V statistic. However, as we increase the memory, we can see that the true density of the V statistic gains more variance, and because of that it gets flatter and flatter. And as it gets flatter, the threshold gets larger, and it diverges from the threshold that we get from our permutation bootstrap. And for the processes with quite large memory, 0.8, the difference is really significant. And we cannot really say that the permutation bootstrap gives us a way to, or insight into what is the actual density of the V statistic. Why is it happening? Why are we failing to mimic the distribution of the V statistic? Well, to see what's going on, we need to look at the similarity matrices once again. So here are the similarity matrices plotted for the random processes rather than for the IID observations. If we put them together to look at the gram matrices, you can see that they've got different structure than the matrices that you get for the IID observations. So what you can hopefully see in this picture is that those matrices get more blobby structure. They are less granular. And the reason for that is that when you take 2 points that are close to each other in random process, they tend to be similar because there is a temporal dependence. And as a result, 2 entries of the matrix that are close to each other also tends to be similar. And this is visually shown as having the same color. And because of that, we can see blobs which have the same color and very slowly as the difference between them grows. What happens if we multiply our gram matrix with the bootstrapping matrix that is, so to speak, totally random, that is generated using this random vector W? Well, the bootstrapping matrix that we get from this vector W, the permutation vector W, is very granular, and as a result, we're losing this blobby structure. Indeed, on the left-hand side, you can see the actual matrix when P is equal to Q, and on the right-hand side, you can see the effect of multiplying this matrix by the permutation bootstrapping matrix. So we do lose some information that you can visually see. We do lose this blobby structure. So it's kind of obvious that we need to come up with some other bootstrapping scheme. And the bootstrapping scheme that we are going to use here is called the wild bootstrap. So the wild bootstrap was proposed in the econometrics literature, and we've adapted it for this work. And in order to come up to have a better bootstrapping strategy, we're not going to generate the vector W that is, like, so to speak, totally random, but we're actually going to generate the vector W to be a process with memory. And since it's a process with memory, the bootstrapping matrix is going to have the blobby structure, and we hope that when we multiply the gram matrix by the matrix with a blobby structure, we're going to recover the blobby structure again, and as a result, get better approximation of the V statistic. So in here, we're generating W as a Markov chain with a probability of switching from one state to the other equal to 0.5, and first state is 1, and the second state is -1. So indeed, if you have a closer look at the actual matrix when P is equal to Q and the matrix that we get by multiplying the actual matrix by the bootstrapping matrix, well, they seem to be the same. Again, this is just an impression, and we'd like to quantify that. And we quantify it by defining, again, the bootstrap V statistic, but now we multiply our gram matrix by the bootstrapping matrix that was created using the random process. Let's see how this bootstrap V statistic, now it's V and W, how well does it approximate the actual V statistic. So again, in a case when memory is small, there is no much difference anyway, and the correct threshold is close to the bootstrap threshold. And recall that now, again, we're feeding our two-sample test with random processes. And now we'll be increasing the memory of our random processes to 0.2, 0.3. Memory was the autoregressive coefficient, so the processes are gaining more memory, and the two thresholds are staying close to each other. And also the histogram of the Bootstrap V statistic, V and W, resembles a lot the density of the true V statistic. And this trend does not, so to speak, finish. You can see that the approximation is also good for the processes with large memory. So now I'd like to talk a little bit more about the application and the experiments that we did. So the method can be used, the two-sample test can be used for the MCMC method diagnostics. What I mean by that is we can, usually in the MCMC methods, we are generating few random processes. The processes that you can see arise as a result of running a Gibbs sampler. And we'll be trying to assess whether the samples that you can observe in a green box have the same distribution. If they do, we'll infer that the Markov chains have converged to the stationary distribution. Should they differ in the green box, we would say that they are still converging and therefore their distributions are different. If we use the permutation MMD test, it turns out that the type 1 error is around 68%, which means that in 68 out of 100 cases, the permutation MMD would say that P is different than a Q, and that's not really the case. If we use the wild bootstrap, though, turns out that the type 1 error is only 6%, and that's what we're expecting. As I've mentioned before, you can use the wild bootstrap for other kinds of statistical tests, in particular for the independence testing. So you can think about independence tests between two random processes, and that's what we did. We took two random processes. One of them was the trading volume of the Dow Jones Index, and the other one was the sounds from the magnetic fields, sounds from the song made by magnetic fields group. So these two are time series, and the question that we ask is whether those two are independent of each other, or if there are some dependency between those two. The independence test that we are using is a Hilbert-Schmidt independence criterion. That's a kernel independence test. And we do get very small p-value, which means that the permutation HSIG indicates that there is some dependency between those two. And that's not really what should be happening. However, if we use the HSIG with the wild bootstrap, we get the answer that is much more expected, I would say. And the answer is no. There is no dependency whatsoever between those two. And with this example of the spurious dependency, I'd like to leave you, and I'd like to thank you for your attention.
Questions?
Yeah, just a question like, when you are saying, because it seems like you are doing a statistical test, and when you reject that test, you can't prove that's equal. So basically, in this case, you just say, you can only say I have no enough kind of information to say they are different.
That's true. I did make a mental simplification in here. You're only rejecting the null hypothesis, and your type 1 error will be always around whatever you set it up to. So there is, in this case, there is always the p-value. You can see at the p-value, and well, this p-value for the wild bootstrap HSIG seems irrelevant. However, the p-value for the permutation HSIG is really small, and you would actually reject the hypothesis that they are independent in most of the cases.
Okay, if no more questions, let's thank the speaker again.
Thank you.
So that concludes this oral session, and spotlights will start again.